Welcome back to our exploration into trigonometry. We're going to be working with right triangle trigonometry in this video. You need to recall in a right triangle, you have one angle that is 90 degrees, and the other two angles are acute, meaning they're less than 90 degrees because a triangle, all three angles sum to 180. So if one is 90, then you only have 90 degrees left with two angles, so they're both acute. Now, a right triangle with an acute angle has a hypotenuse, which is the longest side and is opposite of the right angle, has an adjacent side, which is adjacent to wherever you draw the angle theta, and then you have the opposite side, which is opposite of the angle theta. So it's all in relation to where your theta is. Here in our drawing, we have theta in this corner, but if I was to draw theta in the other corner, then this would become the opposite side because it was opposite that new angle, and this one would be the adjacent side. So it's all relative to your theta. We're going to abbreviate hypotenuse with HYP or H, opposite with OPP or O, and adjacent with ADJ or A. There are 6 trigonometric functions that hopefully you're familiar with. They are sine, cosine, tangent, cosecant, secant, and cotangent. And they're defined for us here where sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and then cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So in this example that we have on a triangle here, we have the sides listed as a 3, 4, 5 triangle, which is it's actually a Pythagorean triple. In this angle theta, opposite is the value of 3 for this side length, and hypotenuse is 5. And so then the sine of that angle theta is 3 over 5. And notice that the units cancel out because you're stacking like units on top of each other. And so we don't have units when we're talking about sine through cotangent. An acronym that people use to remember these trigonometric functions, or just the first 3, is SOHCAHTOA. And that represents sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. For this triangle that we have here on the right, we see that the sine of theta is equal to x over b. So we're talking about, for theta of the smaller triangle ABC, that is x over b. And then for the larger triangle ADE, that would be y over d. And in this case, the angle isn't changing. The angle measurement is the same for the smaller triangle and the larger triangle. These are similar triangles. They are different sizes, but they have the same angle measurements. And so they have angle-angle similarity. And in this case, the sine of theta is equal to x over b, but it's also equal to y over d. And so you could actually use that to solve similar triangle values for side lengths. We're going to focus on special right triangles now. In this case, there is a 45, 45, 90 triangle. We also have a 30, 60, 90 triangle. And in a 45, 45, 90 triangle, what that's saying is these two angles are both 45 degrees. And when your angles are the same measure, then your side lengths are the same measure. So this becomes an isosceles triangle where the opposite and the adjacent are equal, regardless of which 45-degree angle you're talking about. Now, let's say I gave this side length 1. That means that this side length would be 1. We can use the Pythagorean theorem to figure out what the hypotenuse would be. So the hypotenuse would be equal to the square root of 1 squared plus 1 squared, or the square root of 2. And we will use this for the unit circle. Sometimes you see it with xx and x root 2. You can use it to find out the values of various right triangles that are 45, 45, 90. For a 30, 60, 90 triangle, we're going to start out with an equilateral triangle. And in an equilateral triangle, that means that all three sides are the same and all three angles are the same, which means we have 180 degrees divided by 3. Each angle is then 60 degrees. Well, what if I was to draw an altitude straight down, which is a bisector? It would cut that top angle in two, and it would form a right triangle. And so that top angle would cut 60 in two and become 30 degrees. And that is then a 30, 60, 90 triangle. Well, I'm going to draw that over here on the right. And let's use that same idea of calling the equilateral triangle. Let's say that each side length is 2. And so then that small portion would be 1. Now, if I have 1 and 2 as the hypotenuse, I can again use the Pythagorean theorem to say 2 squared equals 1 squared plus that altitude that's missing. And so A is going to be equal to the square root of 2 squared minus 1 squared, or 4 minus 1, which is 3. So a 30, 60, 90 triangle has ratio of 1, root 3, and 2. Here's a table of measures for 30 degrees, 45 degrees, and 60 degrees. And there's these values of root 2s and 3s, and you might be wondering where they come from. But remember, in that isosceles triangle of a 45, 45, 90 triangle, we had side lengths of 1 and hypotenuse of 2. So if I'm talking about a 45-degree angle, let's say this is theta, sine is going to be 1 over root 2. But we always rationalize the denominator. We do not want to have the radical in the denominator, so then we would multiply by root 2 over root 2, and that simplifies to root 2 over root 4, or just 2. So that's where that root 2 over 2 comes from. The cosine is the same thing, because the adjacent is also 1 over root 2. Tangent is opposite over adjacent, or 1 over 1. And then the reciprocal is, remember, hypotenuse over opposite, or root 2 over 1. Adjacent over hypotenuse, or root 2 over 1, and then cotangent is, again, 1 and 1, 1 over 1. For a 30, 60, 90 triangle, let's say we start with the angle of 30 degrees here. Opposite would be 1 over 2, and adjacent would be root 3 over 2. And then opposite over adjacent is 1 over root 3, and again, rationalizing that denominator, which you want to be familiar with because we will do it a lot. That's the square root of 9, which is just 3. So you have root 3 over 3. Same thing for 60. It's just the sine of 60 is root 3 over 2, and the cosine is 1/2. So notice that these values for 30 and 60 are the same. They're just reversed. So 30 is 1/2, and then the 60 is root 3 over 2, and then they swap for cosine. When we get to the unit circle, I've got some tricks to help you remember what the order is. But these values are going to be values that you use all the time. You want to become very, very familiar with them. In trig, we have these fundamental identities, which we can use to help us prove things. We can use it to help us find values. I did say that cosecant is the reciprocal of sine. And so sine of theta is equal to 1 over cosecant, or cosecant is equal to 1 over sine, since they're reciprocals. Secant and cosine are reciprocals, and cotangent and tangent are reciprocals. And you can use either version to help you out, depending on what you're trying to solve. One thing that I like to remember when I'm talking about cosecant and secant is that sine goes with the C. It's not sine and secant reciprocals, it's sine and cosecant that are reciprocals. And then same thing, cosine goes with secant. So you're switching the letters. That's just something you can help, or something that might help you remember. Now, we can use identities to help us find values. Like say I had a right triangle and I knew what sine was, I could then use the identity that cosecant is 1 over sine to find what the cosecant is. We also have what's called Pythagorean identities. And the Pythagorean identities say that sine squared of theta and cosine squared of theta is 1, and tangent squared of theta plus 1 equals secant squared of theta, and 1 plus cotangent of theta equals cosecant squared of theta. Where do these Pythagorean identities come from? Let's solve one of them. Let's start with the first one of sine and cosine. Let's say I have a triangle, and I'm going to call it a right triangle with sides A, B, and C. I know from the Pythagorean theorem that a squared plus b squared equals c squared. And if I divide through by c squared, I get a over c squared plus b over c squared equals 1. For this angle theta, a over c is sine, opposite over hypotenuse. So that is sine squared of theta. B over c is the cosine, and we have it squared of theta equals 1. And you can use those ideas to help you prove tangent squared of theta plus 1 equals secant squared of theta, and 1 plus cotangent squared of theta equals cosecant squared of theta. Now, notice that I wrote it with sine and then squared in between the sine and the theta. It's common practice that when you're writing a trigonometric identity to a power, you put the power up after the sign. So that's the same thing as saying sine of theta to some power, but this the way that we write it is we write the n in between, we write the power in between the sine and the theta. And it's also important that you don't just write sine equals something. Sine is irrelevant without an angle. You need the sine of theta. So anytime you're writing sine, it's very important that you write down theta as well.